Welcome, everyone. I'm excited to welcome you to today's presentation on the fundamentals of respiratory physiology and gas exchange. The title of our talk is Fundamentals of Respiratory Physiology and Gas Exchange, with a focus on understanding how ventilation works, the composition of gases, and the dynamics of partial pressures. Today, we'll explore how our respiratory system functions to facilitate gas exchange, which is essential for life. So, let's get started and dive into the fascinating processes that keep us breathing and alive. Let's dive into the fundamentals of respiratory physiology and gas exchange by focusing on understanding ventilation. Ventilation is essentially the process of moving each breath, or tidal volume, in and out of the lungs. During this process, fresh air enters the lungs and mixes with, and replaces, some of the air that was already there. This exchange is vital for maintaining proper respiratory function. Now, the pattern of how we breathe, the depth and frequency, is known as the ventilatory pattern. This pattern plays a crucial role because it can significantly influence how efficiently gases like oxygen and carbon dioxide are exchanged. When the ventilatory pattern is well regulated, it ensures that the body receives enough oxygen and removes carbon dioxide effectively. Moving to the next point, when we talk about air replacement dynamics, it's important to understand that fresh air doesn't just fill the lungs uniformly. Instead, it replaces some of the air already present, which is key to keeping our respiratory system functioning properly. Finally, regarding tidal volume and gas exchange, not all of the air we breathe in actually reaches the alveoli, the tiny sacs where gas exchange occurs. This highlights the importance of understanding how air is distributed within the lungs, because only the air reaching the alveoli participates directly in exchanging oxygen and carbon dioxide. So, in summary, ventilation involves more than just breathing in and out. It's about how effectively we move and distribute air to optimize gas exchange throughout the lungs. Let's start with atmospheric pressure at sea level. The standard value is 760 millimeters of mercury, or mmHg, which is also called torr. This is a key reference point that scientists and meteorologists use for various measurements. Moving on to the primary composition of air, it's mostly nitrogen and oxygen. These two gases make up the bulk of what we breathe every day. There are also trace amounts of argon, carbon dioxide, and a few other gases, but nitrogen and oxygen are the main players. They form the breathable atmosphere that supports life on Earth. Now, when we talk about the composition of air at sea level, it's important to understand the concept of partial pressures. The total atmospheric pressure isn't just a single value. It's actually the sum of the partial pressures of all the individual gases present. Each gas contributes to the overall pressure based on how much of it is in the mixture. This idea of partial pressures is fundamental because it explains how gases exchange in our lungs and tissues. Each gas moves according to its own partial pressure gradient. So, understanding these concepts helps us see how gas exchange works efficiently in our respiratory system. Let's explore the fundamentals of respiratory physiology and gas exchange by focusing on total pressure in gas mixtures. The total pressure of a gas mixture is simply the sum of the partial pressures of each individual gas present. This concept is essential because it helps us analyze the composition of gases in different environments, whether in the atmosphere or within the respiratory system. Now, moving on to Dalton's law, which provides a clear explanation of how these partial pressures work. Dalton's law states that each gas in a mixture exerts a partial pressure that is proportional to its fractional concentration within the mixture. This means that if a gas makes up a larger proportion of the mixture, its partial pressure will be higher. This principle is fundamental for understanding the behavior of gases in the respiratory system. For example, it helps us understand how oxygen and carbon dioxide are transported and exchanged in the lungs. When we think about gas exchange, knowing the partial pressures involved allows us to see why gases move from areas of higher partial pressure to lower partial pressure, which is the basis for diffusion. By understanding these concepts, we gain a deeper insight into how our respiratory system functions efficiently ensuring that oxygen gets into our blood and carbon dioxide gets out. Dalton's law provides a valuable framework for studying these processes and the movement of gases in our body. Let's take a closer look at the partial pressures of gases at sea level, starting with nitrogen. Nitrogen makes up about 78% of atmospheric air, which is quite significant. To find its partial pressure, we multiply 0.78 by the total atmospheric pressure at sea level, which is 760 millimeters of mercury. That calculation gives us approximately 592.8 mmHg for nitrogen's partial pressure. This value is important because it influences how nitrogen behaves in our respiratory system. Moving on to oxygen, it comprises roughly 20.93% of dry atmospheric air. Again, to find its partial pressure, we multiply 0.2093 by 760 mmHg, resulting in about 159.6 mmHg. This relatively lower partial pressure compared to nitrogen explains why oxygen diffuses into our blood more readily. Understanding these partial pressures is fundamental because it helps us grasp how gases move during respiration. The differences in partial pressures between the alveoli and blood drive the gas exchange process. So, by calculating these values, we can better understand the mechanics behind how oxygen enters our lungs and nitrogen remains mostly inert in the bloodstream. This calculation also highlights the importance of atmospheric composition in respiratory physiology and how it influences our body's gas exchange efficiency. Let's discuss how temperature and humidity impact gas pressure in the respiratory system. First, water vapor exerts its own partial pressure, known as pH2O, which depends solely on temperature and humidity levels. This means that as temperature or humidity change, so does pH2O, influencing the overall gas pressure dynamics within the lungs. Now, when we breathe in, the inspired air is warmed to body temperature, which is about 37 degrees Celsius, and it becomes fully saturated with water vapor, so 100% humidity. This process is essential because it conditions the air, making it optimal for gas exchange in the lungs. At this temperature, pH2O remains constant at around 47 mmHg. This stability is really important because it helps maintain consistent respiratory function, ensuring that gas exchange proceeds smoothly without fluctuations caused by changing water vapor levels. Finally, water vapor pressure doesn't just stay passive. It actually reduces the partial pressures of other gases in the lungs. This reduction alters the composition of gases available for exchange during respiration, which is a key point when considering how gases move efficiently across the alveolar membranes. Understanding these interactions helps us see how temperature and humidity are critical factors in maintaining effective gas exchange and overall respiratory health. Let's start by considering the atmospheric pressure at sea level, which is 760 mmHg. This is the total pressure exerted by the air around us. Now, when we breathe in, the air gets humidified in the lungs, and water vapor adds to the mix. If we subtract the water vapor pressure, which is about 47 mmHg, from the total atmospheric pressure, we get an adjusted atmospheric pressure of approximately 713 mmHg. This adjustment is important because it tells us the pressure of the dry gases before they get humidified. Inside the lungs, water vapor pressure remains steady at 47 mmHg, and this water vapor mixes with the other gases. Interestingly, even with this humidification, the total pressure of all gases in the lung still sums up to 760 mmHg, the same as the atmospheric pressure at sea level. Understanding this balance is crucial because it influences how gases exchange across the alveolar membrane. When we talk about the partial pressures of gases in the airway, we're really looking at these adjusted pressures, which account for water vapor. This helps us understand the driving forces behind oxygen and carbon dioxide movement during respiration. So, in essence, the humidification process slightly alters the pressures we consider, but the overall pressure remains constant at sea level, maintaining the gradient needed for effective gas exchange. Let's take a closer look at how we calculate the partial pressure of oxygen, or PO2, in the airways. First, for dry atmospheric air, we know that oxygen makes up about 21% of the atmosphere. So we multiply 0.21 by the standard atmospheric pressure of 760 millimeters of mercury. That gives us approximately 159.6 mmHg. This is the PO2 in dry air before it enters the respiratory system. Now, when air is humidified as it passes through the airways, water vapor adds to the total pressure, which effectively reduces the partial pressure of oxygen. To account for this, we subtract the water vapor pressure, about 47 mmHg at body temperature, from 760 mmHg, leaving us with the pressure of dry gases. Then, we multiply 0.21 by this adjusted pressure, which results in roughly 149.7 mmHg. This difference highlights how humidity impacts oxygen availability in the respiratory tract. Understanding these calculations is key to grasping how oxygen moves from the environment into our bloodstream, especially considering the various factors that influence gas exchange in the lungs. Now let's look at how we calculate the partial pressure of oxygen, or PO2, using this simple formula. PO2 equals the fraction of inspired oxygen, PhiO2, multiplied by the difference between atmospheric pressure, Pb, and water vapor pressure, pH2O. In this example, we're considering an PhiO2 of 50%, which is 0.5, and an atmospheric pressure of 760 mmHg, with water vapor pressure at 47 mmHg. So plugging those numbers in, we get 0.5 times 760 minus 47, which equals 356.5 mmHg. This value, 356, 5 mmHg, is the estimated PO2 at 50% PhiO2. Understanding this calculation is crucial because it helps us determine how much oxygen is available in the alveoli for gas exchange. And of course, it ties back to the overall theme of respiratory physiology, how oxygen moves from the environment into our blood and tissues. Now, let's look at how we calculate the partial pressure of oxygen, or PO2, in the lungs. The formula we use is PO2 equals PhiO2 times the difference between atmospheric pressure, which is Pb, and water vapor pressure, pH2O in this case. PhiO2 is 0.28, representing 28% oxygen. The atmospheric pressure at sea level is typically 760 mmHg, and the water vapor pressure in the lungs is about 47 mmHg. So, when we multiply 0.28 by the difference of 760 minus 47, which is 713 mmHg, we get approximately 199.64 mmHg. This calculation is crucial because it helps us understand how much oxygen is available in the alveoli for gas exchange. Now, considering the clinical question here, what is the PO2 when the patient is breathing 28% oxygen? The answer, as we've seen, is about 200 mmHg. This kind of calculation is fundamental in assessing oxygenation status and guiding clinical decisions, especially in cases where oxygen levels are compromised. Remember, understanding these principles connects directly to how we evaluate respiratory function and optimize patient care. Let's take a closer look at how we calculate the maximum oxygen partial pressure, or PO2, when inhaling pure oxygen. The key formula here is PO2 equals PhiO2 multiplied by the difference between atmospheric pressure and water vapor pressure. In this case, PhiO2 is 1, which means 100% oxygen. The atmospheric pressure, Pb, is 760 millimeters of mercury, and the water vapor pressure, pH2O, at body temperature is approximately 47 millimeters of mercury. When we do the math, this tells us that the maximum PO2 achievable with pure oxygen inhalation is essentially 713 millimeters of mercury. This represents the highest partial pressure of oxygen we can expect in the lungs under ideal conditions. It's a useful concept because it helps us understand the limits of oxygen transfer in the lungs when giving pure oxygen. Remember, this value is theoretical and assumes perfect conditions without any barriers to gas exchange. This calculation underscores the importance of knowing the maximum potential for oxygen delivery, especially in clinical settings where oxygen therapy is critical. It also ties back to our overall theme of understanding gas exchange efficiency and how we optimize oxygen delivery to tissues. Let's talk about the fundamentals of respiratory physiology and gas exchange, focusing on minute ventilation today. Minute ventilation, or VE, is essentially the total volume of air that enters or leaves the lungs in 1 minute. It's a crucial parameter because it helps us understand how effectively the lungs are ventilating. Clinically, we measure VE by summing up the exhaled tidal volumes over a 1-minute period. The result is usually reported in liters per minute, which gives us a clear and measurable way to assess ventilation status. Now, when we classify ventilation, we often focus on VE itself, but it's important to remember that VE doesn't tell us how much of that air is actually participating in gas exchange. That's a key point because high ventilation doesn't necessarily mean efficient gas exchange is happening. To calculate VE, we use the simple formula. VE equals tidal volume times respiratory frequency. Tidal volume is the amount of air moved with each breath, and respiratory frequency is how many breaths we take per minute. This formula highlights the relationship between how much air we move with each breath and how often we breathe. Understanding these concepts helps us see the bigger picture of respiratory efficiency and how various factors can influence gas exchange in the lungs. Now, let's look at an example to understand how tidal volume and respiratory rate work together to determine minute ventilation. Here, the given tidal volume is 500 milliliters, which is the amount of air moved in or out of the lungs with each breath. This is a typical resting value for many individuals. Next, we have the respiratory rate, which is 12 breaths per minute. This tells us how many breaths a person takes in a minute during normal breathing. To find the total amount of air exchanged per minute, or the minute ventilation, we multiply the tidal volume by the respiratory rate. So, 500 ml per breath times 12 breaths per minute equals 6,000 milliliters per minute. Since 1,000 milliliters equals 1 liter, this converts to 6 liters per minute. This is a key concept because it shows us how these two variables, tidal volume and respiratory rate, combine to determine overall ventilation. Understanding this helps us appreciate how the respiratory system adapts to meet the body's oxygen demands and remove carbon dioxide efficiently, which is fundamental when studying respiratory physiology and gas exchange. All right, let's walk through this practice question on minute ventilation. So, using the formula VE equals VT times F, where VE is the minute ventilation, VT is the tidal volume, and F is the respiratory rate, we can calculate the total amount of air moved in a minute. In this example, we have a tidal volume of 800 milliliters and a breathing rate of 8 breaths per minute. When we do the math, multiplying 800 ml by 8, we get a total ventilation of 6.4 liters per minute. Now, if we look at another scenario where the tidal volume is 400 milliliters, but the respiratory rate increases to 16 breaths per minute, the total ventilation still comes out to 6.4 liters per minute. This highlights a key point. Different combinations of tidal volume and respiratory rate can result in the same overall ventilation. It emphasizes the importance of understanding how the body can adjust these parameters to maintain adequate gas exchange, which ties back into how our respiratory system functions efficiently under various conditions. Let's look at a practical example to understand how to calculate minute ventilation, or VE, which is a key concept in respiratory physiology. The formula we use is VE equals tidal volume, or VT, multiplied by the respiratory rate, or F. For instance, if we have a VT of 600 ml and a breathing rate of 10 breaths per minute, we simply multiply these two numbers. So, 600 milliliters times 10 breaths per minute gives us a VE of 6 liters per minute. This means that, under these conditions, the total volume of air inhaled or exhaled in 1 minute is 6 liters. Now, Let's see what happens if we change the numbers a bit. Suppose the VT is 500 ml and the respiratory rate is 12 breaths per minute. Again, we multiply these, 500 milliliters times 12 breaths per minute. That also results in a VE of 6 liters per minute. This example highlights that different combinations of tidal volume and breathing rate can produce the same minute ventilation. Understanding this helps us see how the respiratory system adjusts to meet the body's oxygen demands and remove carbon dioxide efficiently. So always remember the simple formula. VE equals VT times F. It's a fundamental concept that ties directly into how we evaluate respiratory function.